Okay, so we're going to finish this lecture off about polygenic indexes. We're going to talk about some practical details about how we actually build these things. We're going to talk about some limitations with polygenic indexes, and then go through some applications. Are there questions first about anything we discussed before lunch? Okay, good. Let's just okay, yeah, we're working. Okay, great. So, so there's a problem, right? We talked about how these polygenic indexes are supposed to represent the coefficients on the additive SNP factor, which we were calling little b, right? But when we have the data that we have to construct these polygenic indexes is little b GWAS. Why is this a problem? What's the difference between GWAS estimates and these little b's that we're trying to get? So it's why would being based on a meta-analysis cause a problem? Yeah. So well, a meta-analysis would make us more precise, right? I guess because the issue is we can't. I mean, a meta-analysis allows us to combine data sets. I mean, there is one problem that's just due to noise, right? Like, it is an estimate, and so it's not perfect. We talked a little bit about the noise, but there's also an issue. Like, even if we had infinitely large samples and noise wasn't a problem, there's also going to be a difference between these b's and the b's we would get from a GWAS. What's the difference? Oh yeah, there you are. Oh, I was really sneaky. Good job reading. Why didn't any of you raise your hands when the answer was right here? Okay, but yeah, this is the idea. So remember that if we did a GWAS, the GWAS coefficient for SNP1 is going to capture the effect of SNP2 and 3 and 4, any SNP that's in LD, right? And so if we used the GWAS coefficient for SNP1 in our polygenic index, and then we use the GWAS coefficient for SNP2, SNP2 is also going to capture the effect of SNPs 1, 2, 3, 4, anything that's in LD, right? And we're going to be double counting the signal. There you are. Now it's not even grayed out anymore. So we're going to so like, areas where there are really high LD scores, areas where just, really long run blocks, LD blocks, where things are correlated, we're going to be double counting that information, double, triple, way over counting relative to areas where the LD blocks are smaller. And so just arbitrarily, we're going to just be misassigning signal in ways that aren't optimal, right? And we want, these beta J is the optimal thing. And so we want estimates of BJ versus BGWAS, right? So that's the problem. So the overarching problem is that we're not accounting for LD correctly. And so ideally, a method to estimate polygenic indexes is going to think about LD. So there are maybe a handful of potential solutions that we might do. Some are more common than others. And so one that's actually still quite common is this idea of pruning. So you could imagine, you remember when we do a GWAS, we also have this issue of LD making us not want to double count signals. And so what we did then is we said, well, let's just take the most significant SNP, and then we're just going to ignore any SNP that is an LD with that SNP. And then, as we're calculating our lead SNPs, we then look for the next most significant SNP that's not in LD with the SNP that we found already. And we can just identify an independent set of SNPs. And so there's no LD between them, or very little LD between them, at least. And then there's not going to be a risk of overcounting. And so you'll make a score based on a small set of independent SNPs when you're done. What might be a limitation of doing pruning like that? Why will this mean that there's signal that we're missing?
It's on the slide.
Is it on the slide again? Look at that! I need to stop putting the grayed out stuff. It's just such a spoiler. Okay, but why does it matter that k is smaller then? Like, what does that do for us? That's not on the slide.
More error. Like this accurate.
Well, smaller k actually means that there's less error. Because remember, the error in the polygenic index is the result of summing the error over lots of SNPs. And so if we're just looking at k SNPs, where k is much less than all of the SNPs, there's actually less error. Yeah.
Well, there could be like one of these like SNPs that you took out, and they could still have like a part of variability that they explained that one that you took out. Right?
Yeah, exactly. There's SNPs that, if there are two SNPs that both have a causal effect, and maybe they're in LD, but they're only in weak LD. Maybe they're correlated at like 0.3 or something like that. Like, we'll capture part of the effect of that SNP that we've dropped, but not the whole thing. This is also related to the way, the reason that if we reduce the set of SNPs, it reduces the SNP heritability. So if we think about, what's the SNP heritability of the, of the k SNPs that we select through this pruning algorithm, then, that's going to be lower. And because the SNP heritability is lower, the R squared will be lower. Is that a question or just a? No, OK. Great. Great. I think that's all I wanted to say about pruning. So alternatively, we could do something like KOJO. So we talked about KOJO, I think, super briefly earlier. And the idea of KOJO is we're starting with our little B GWASs, right? And we can work out, if D represents the correlation matrix of the genotypes, you can do a little bit of work. And it turns out that the B GWAS is actually equal to the B hats that we want, left multiplied by the correlation matrix. And so given this relationship, we could just left multiply by D inverse. And that tells us how we can go from B GWAS to just the B's that we want. So that's slick. That's kind of cool, right? There's a few things that make this hard. One of them is that these correlation, if you have two SNPs that are perfectly correlated, then this D matrix isn't invertible. And so you can't do this if there are sets of SNPs in your data that are perfectly correlated, or sets of SNPs that are collinear together. All right? And so you'd first need to then maybe reduce your set of SNPs to one such that D is full rank, so you can invert it. There's another problem too, though, related to where this D comes from. Right? So this D is supposed to represent the LD patterns in your discovery sample. But if we're doing GWAS, we're using GWAS summary statistics, part of the reason that maybe we want to do something like this is because we don't have access to the actual data that the summary statistics came from. If we did have that data, we could just calculate this D from the individual level data that we had, and it'd be great. But we usually don't have it, and so we have to rely on reference samples. And so we might take the publicly available 1,000 genome data, or or maybe some other reference sample, and calculate D this way. From a reference sample, that seems like a good solution. What's the problem with that solution? What could go wrong? It's let's say that our GWAS comes from Arkansas, and this reference sample comes from someplace else.
Can you repeat?
So I'm saying that the issue is that we're going to be using some reference sample to calculate this D matrix, this correlation matrix. And that may, and it's going to be a different set of individuals than was used to calculate the GWAS summary statistics.
So if there are different ancestries, maybe the LD patterns.
Yeah, so that would be a big problem. So let's say that our summary statistics came from East Asia, and then we use a South African reference data set or something like that. Those aren't going to resemble each other at all. So this is just going to be garbage. But even if you have samples that are pretty close, you have two European samples, there are subtle differences in even within samples with homogeneous ancestries, what we would consider homogeneous, right? And it turns out that this approach can sometimes blow up, especially if we're looking at kind of rare SNPs. You know, if you're looking at common stuff in correlation, not much can go wrong, because like if the true correlation is like 0.45 and you estimate it to be 0.46, like that doesn't sound so bad. But if the LD is actually, you know, 0.01 and you estimate it to be, you know, 0.1, like that, you know, that's way off in kind of comparison. And sometimes things like this happen when you do KOJO. And so you have to be careful about that. In practice, this is not commonly done. So this is a thing that you see sometimes in some settings when there's a specific thing that, you know, a person wants to know. But in general, you don't see people making polygenic indexes using KOJO. Yeah.
It seems like you're describing this as a unique weakness of KOJO, but I feel like it could come up anytime you're relying on a publicly available reference sample, right?
Yeah, that's true. So like there's a lot of methods that require using publicly available reference samples, and that's always going to be a problem. With KOJO, it turns out that it's like especially sensitive to these kinds of problems, especially when you're looking at, you know, rare SNPs or SNPs where the correlation is either very high or very low. And so that's why, you know, I bring it up here especially because it's particularly sensitive to that problem. Yep.
I haven't thought this through all the way, but I feel like, so since people use the UK Biobank for so many analyses, is there any value or possibility in making like a special UKB LD matrix that's like just for that population?
That'd be a great idea. The part of the issue, so for something like this, that's great because it's the, you know, you actually want to know the correlation matrix of the genotype SNPs. Some methods require knowing what the LD matrix is for, you know, a much wide, you know, sequencing kind of data. They're releasing at least the exomes for a big chunk of UKB soon, and so, you know, it might be possible then. With, you know, but in general, the limitation up until now has just been some applications required sequencing data to do something like this because we needed to be able to look quite into the very rare space.
Okay.
But I agree. For something like KOJO, if you wanted to do KOJO and you're using a GWAS that's just based on the UK Biobank, you know, ideally you would use the LD matrix that's just based on the UK Biobank too. It's going to be a lot less sensitive to these kinds of problems we're talking about.
For some analyses, that is actually available now.
Oh.
Sweet.
It's available.
Yeah.
But if the UKB is imputed using, or I don't know if the UKB is, if they use like 1,000 genomes to impute it, but when you just recapitulate the LD and the...
I guess it depends on how good the imputation is, right? Like you could imagine that the reference samples are good enough for imputation, and then even if the LD is slightly different between the two groups, just because of the balance of people from different regions. Like just the way the imputation works, it's not like a linear thing. If the actual haplotypes that are available in the UK Biobank are present in the 1,000 Genome Project, then you could impute at least the common variants quite well, and then recover the LD matrix that's more relevant to the UK sample.
I see. Okay.
Good. So this third approach is the one that is what I prefer and what everyone should prefer. So these are a set of Bayesian approaches that account for LD, and there's a handful of these. I've listed 3 here. So there's LD Pred, which was kind of like the only game in town for a while. There's also PRSCS, which is, I think, the method that you're going to be taught here. BEST-BAZAR, which is just another approach. You know, these are all similar. They differ in a key way that we're going to talk about in a second. I think we chose to teach you guys PRSCS because I think it's a bit more user-friendly than some of these other. It's a little less error-prone than these other 2 methods. But all of them are quite common. You know, when you do horse races against each other, it's not totally clear that like any one of these has a big advantage over another. So they're all, you know, they're all fine. I wouldn't get mad if I saw anyone using any of these. Okay, so let's talk about Bayesian approaches a bit more in detail. So the idea is I'm going to be thinking kind of like a Bayesian approach, right? What we would like to know is what do we think the B is? You know, what's our best guess of what B is given the GOS coefficients and given LD patterns? Right, so like this is just a very short way, like this is exactly what we want, right? This is a mathematical way to express what we wish we had. And so by Bayes' rule, we want to know what's the distribution of B given the GWAS and LD. This is just this written by Bayes' rule. So this thing here is the likelihood function. So this is given the true B's, what do we expect the GWAS summary statistics to be. And this is just going to be a function of sampling. So this is pretty easy. But then we have this term here is what do we think the little b's are? What do we think is the distribution of effect sizes that we see? And so we have choices. And so I'm going to talk. So this is the way that the three methods differ. Is in the assumption about what the distribution of actual effect sizes are. So LD-Pred uses the spike and slab prior. We talked a little bit about that. And so the idea is that we think that the little b's are, there's some probability pi that they have exactly 0 effect. That's the spike. And then there's some probability 1 minus pi that is drawn from a normal distribution. That's the slab. It looks like that. Right? And so this seems pretty sensible. We talked about this the other day. And this is what LD-Pred does. This has as a special case just having a normal or a Gaussian prior if we assume that pi is equal to 0. And so when you run this, you have to make a choice about what pi is and also, I guess, what tau is. In practice, when we've run this, it doesn't do significantly better by just saying that this is 0 and using a normal prior. But maybe you can do a little bit better by using something more sophisticated to pick your pi. But this is LD-Pred. Then there's PRCS, and this one's way more complicated. So the problem with the spike and slab priors, some people, is this issue of thick tails. And so this normal distribution here decays very quickly. And so it means that you're unlikely to get SNPs that have very big effect sizes. And so maybe we want something that decays less quickly. And so that's what these people developed. And so they say, OK, well, the B's, they're drawn from a normal distribution with 0 mean. But the variance itself is a random variable. And so it's going to be some constant phi times this gamma, or psi. And psi is distributed gamma. And then it goes one layer further. And this gamma has parameter a delta. And delta itself is also gamma. Right, so they're just making this random down several layers. What this means in terms of what the shape of this distribution looks like is it looks kind of like a normal distribution that's a bit more peaked, and it decays a little bit less quickly. And so you can just think of it as this is kind of a normal that's been stretched out in the tails a little bit. Okay, so that's so there's two parameters you need to choose here. You need to choose A and B. A and B determine kind of how likely it is that things exist out in the tails. This looks very complicated. So you're like, why would we ever do this? This looks crazy, right? It turns out that just computationally, it's a bit easier to work with these smooth. This has a big spike at 0, and kind of this disjointness of the distribution gives it bad computational properties. And so they said, let's do this thing. It'll be computationally a lot simpler to run. It'll crash less frequently and things like that. So that's why you'd maybe use PRSCS. SBayes-R is kind of like a spike and slab on steroids. In the paper, they write it like super generally. Like they say it can be a mixture of however many normals that you want. But they say, what we recommend, because this seems to work the best, is 4 normals, just like this. So there's some probability that it has a 0 effect, some probability that there's a bunch of SNPs that have just a very small effect. So sigma. These should all be normal distributions with mean 0 and variance equal to what's here. I just realized. This would be a very strange genetic architecture. But yeah, I'll fix this later. This is the, so this should be normal, mean 0 with variance equal to this. And so this means this has a very small variance. And so these are going to be a bunch of SNPs that cluster very close to 0. They have very, very, very little, a very, very small effect. Then there's some that have kind of a medium-sized effect and some that have a big effect. And so this term here is going to catch the thick tails. This is going to capture the things that maybe have big effects. But there's just generally a big cluster of things close to 0. And then, so you do need to pick these probabilities, how much is being weighted on each of these things. And then you also need to pick just generally how spread out this is in general. So like, heritability will kind of determine what these sigmas are. and then kind of how thick the tails are going to determine what these pi's are. That's S-Bayes-R. It also works pretty well too. In fact, I mean, in the EA4, S-Bayes-R is slightly better. I think I told you guys that in AdHealth, the predictive power of the polygenic index for educational attainment is 16%. If you use S-Bayes-R, it's 17%. That's better. It's not but not game changing. And it's again, just generally like what we see with these kinds of things. Sometimes different methods do a little bit better than others, but it's not like gonna get you to like 90% or something. Happy? So something to keep in mind is, this is based on some of the questions that people were asking. I think that these Bayesian polygenic indexes use every SNP that's genotyped. They use every single one. So we're not just focusing on only the things that are genome-wide significant or a set of pruned SNPs. And the reason for that is because even if a thing, we're only well-powered to find a subset of the actual associated SNPs. And so by throwing out things that like have a p-value that's too high, like it's perhaps wasteful. There actually might be signal there that we can use. And so by using all of the SNPs, in practice that seems to work out pretty well, that and theoretically you could actually work out that you would expect that these approaches that use all SNPs to be more predictive than ones that are just pruned down to a subset of significant things. Great. So that's the sort of theory behind the I guess it's not practical because you guys are going to act, you didn't make any indexes yet, but you're going to. Or maybe you have, but you're going to do it here. So now let's talk about some limitations of polygenic indexes. So the first one is related to the error. So I told you already that polygenic indexes you can think of as the additive SNP factor plus some noise. And I told you that as a result, what that means is that the R squared is going to be attenuated. It's going to be smaller than the R squared that you would get if you actually used the additive SNP factor. It also has effects on interpreting, if you use the polygenic index in your research, how do you interpret the beta on the polygenic index in your regression? And it turns out it's a bit tricky, right? So in a typical application, you have some regression, and you regress some outcome W on the polygenic index, plus a bunch of other things. Maybe interacting the polygenic index with some stuff, but this is kind of the basic idea of what we're doing. So when we create these polygenic indexes, we often standardize them to be variance 1. But the polygenic index has this noise, and so we're standardizing it like we're baking the noise into it, right? And so then how do you interpret that, right? Like a 1 standard deviation increase in the polygenic index, what does that even mean? Because some of the increase might be due to an increase in the additive SNP factor, but some of it might just be increased due to the noise. And so it's a bit fuzzy. It's especially tricky because the amount of attenuation, the amount of noise, is going to vary by what GWAS that you use. And so let's say that I use the EA3 polygenic index for my analysis, and then someone else uses the EA4 polygenic index in their analysis. Like how do you compare those results? Because they have different amounts of noise, they've been scaled by different numbers. It just doesn't make, it's just very difficult. And so what we're going to propose here is that what we should actually be doing, ideally what we would do, is report all of our results with respect to, in effect, sizes of standard deviations of the true PGI. Ideally, if we had an infinite sample size, that's what we would be using. And so it's probably valuable in terms of interpretability and comparability across studies to try to write things with respect to the units of this true PGI. So, so we could say that the coefficient is what's the effect of the true PGI increasing by 1 standard deviation unit. I guess I talked about this a little bit, but let's think about what the error does to our studies. So so it depends on actually what covariates are included. So if you have some covariates in your study, or no covariates at all, and they're uncorrelated with the PGI, I'm not going to work through the math, but I'm just mostly going to give a bit of intuition here, just so we can understand where things are coming from. Well, this is basically classical measurement error, right? The error in the PGI is the sum of a bunch of measurement error coefficients, and by the central limit theorem, those are normally distributed, and so the sum of the normally distributed error across all SNPs is also going to be normally distributed. So this is like, you know, beautiful, perfect classical measurement error, which means this is going to lead to attenuation bias. And the amount of bias that you would expect to see is pretty predictable, right? So if gamma is the coefficient on the polygenic index, then if the covariates are uncorrelated with the polygenic index, then that's going to be approximately equal to just the covariance of, you know, and we already worked through this math actually on a previous slide. So this is, but you can notice here in the denominator, in the numerator, we just have the covariance of the outcome with the additive SNP factor, like the thing that we want. And in the denominator, we have the variance of the additive SNP factor, the thing that we want, but then this noise term that we don't want, right? And so because this is positive, the denominator is going to be too big, which means this whole thing is going to be too small. It's going to be biased downwards, or I guess biased towards 0. I guess this thing could be negative in the numerator. So that's kind of basically why attenuation bias works. But you sort of think, well, you know, if we know how much noise there is, how much error there is in our polygenic index, you could just subtract this out of the denominator, and it would correct it. It would solve all of your problems. And so, you know, so that's maybe a nice thing that we could do that would then move things into the units of the additive SNP factor instead of in units of the polygenic index. It gets more tricky if the covariates are correlated with the PGI. The reason for this is if you have this noisy PGI measure, then your covariates, which are correlated with the true additive SNP factor, are going to like slurp away some of the signal from the PGI. And as a result, you're going to see even further attenuation in the coefficient associated with the PGI, and you'll see an inflation on the coefficients associated with the covariate. And I'm in the example I'm speaking about here, I'm assuming everything's positively correlated with everything else. So, and so the measurement error in the PGI, in this case, in a model that has covariates that are correlated, that's messing up all of your coefficients, and all of them will need to be corrected. So as part of the PGI repository project, we wrote a piece of software that does this correction. And so it will correct things in, Grant actually wrote this software. So if you have questions about it, and John, who you'll meet next week, hopefully. Yeah?
The covariate here means just age or sex, those basically
Yeah.
like a parent or DS or whatever.
Yeah, so you could imagine, so I'm going to give an example later where they wanted to control for like parental education. So like, you know, so that would be an example where, you know, your PGI is going to be associated with your parents' education. And so such a study is, you know, the coefficients are all going to be messed up if there's error in your PGI. Yeah. So there is a piece of software. You can look it up. We talk about it in the Becker et al. Polygenic index repository paper, where you feed it the results of your analysis that includes a PGI and even interactions of the PGI with other covariates. And then it spits out, you know, what the corrected estimates would be in units of the additive SNP factor. So hopefully that's useful in terms of like, you know, correcting your results to be in more interpretable units.
Yeah, I was wondering whether like this new PGI versus the PGAs for at least of phenotypes that we had before, for instance in the HRS, did you find like substantial like differences between the previous and?
So you're talking about, so the HRS had released PGIs for a handful of phenotypes just internally, but there also were participants in the PGI repository, and so they've also released the PGIs that we produced. I haven't done a comparison. I imagine they're really, really similar. Because like, again, all of these methods tend to be quite similar. You don't see really big differences, no matter what assumptions you make and things like that. I guess you could do a comparison. They're all there, but just practically, when we've done internal comparisons of like what happens if you use PRSCS versus SBazar versus LD-Pred, and what happens when you restrict to HapMap3 SNPs versus they're just little changes generally. Yeah.
Maybe I misunderstood the question, but our GWAS N is much bigger. From that point of view, the repository PGI is better.
Oh yeah, so David was saying that one big difference between the PGIs that we make versus the ones that were released there is that in a lot of cases we had additional data, usually from 23andMe, and so our sample size was much bigger, and so our PGI was generally more predictive than the one that was available before. So there are differences in that sense.
But not by like adjusted versus unadjusted.
Not by what?
The one that corrects for this.
Oh yeah, so this correction isn't about correcting the PGI. This is about correcting regression results that use PGIs. So you would take any PGI from whatever source you want to use. You do some analysis where the PGI is one of the right-hand side variables, one of your covariates. And then you have coefficients associated with that regression, and you want to correct those coefficients. But the PGI, you're not actually changing the PGI at all. Yeah, good question.
Sorry, you said that including the covariate will mess up the coefficient in that regression.
I'm saying that if the covariate is correlated with the PGI, and the PGI has error, that error will mess up the coefficients. I'm going to give an example. Maybe this will make it kind of more clear. Is that OK? So there's a paper by Papa George and Tom. This example is also in the Becker et al. Paper. And they had a bunch of analyses in that paper, but I'm going to focus on two of them. So in the first one, they took the educational attainment PGI, and they regressed it on, I think this is just educational attainment, right? But on educational attainment. And so when you just do a simple regression, I guess they had a handful of controls probably. But when you regress the PGI into education, the coefficient associated with that PGI is about 0.8. And then they said, OK, let's do the same regression, but let's add father and mother's education as control variables. And the idea was they wanted to know how much of this association is being driven by parental education pathways. It was sort of the underlying idea behind the question. And they saw here that there was actually a pretty significant 25% or something like that. There was a pretty sharp attenuation in the coefficient on the EA PGI once you added parental controls. And so you might come away from that thinking, oh, that must mean that this is an important, parental education is an important pathway. So that's maybe one takeaway they took from that. What they also did is they did a G by E study. And so they looked at how likely it was that you graduate from high school. They had as controls the EA PGI. They had a control for family SES. And then they also did an interaction of the two. And so the interpretation here is that the EA PGI is positively predictive of whether or not you graduate from high school, not surprising. Family SES is also positively predicts whether or not you graduate from high school, not very surprising. But there's a negative interaction here, which means that there's maybe some kind of substitutability. People who are in high SES households, an increase of 1 standard deviation in the PGI had a smaller effect on their rates of high school completion than a person in a low SES household. So maybe family SES is kind of filling in some of the gaps or something like that. But they see the opposite for college. So the EA PGI positively predicts college, SES positively predicts college, but they have a positive coefficient here on the interaction here. So this, it's in the opposite direction. And so for high levels of education, their argument is that, oh, well, maybe these are complements. And so if you both have a good PGI draw and a good family SES draw, then those things are going to work together to make you go even further. Right? So these are the uncorrected baseline results. Now let's think about what happens when we have a correction. So in this simple result where there's no covariates at all, unsurprisingly, the coefficient, once you correct it, goes up. And this is again because there was attenuation bias here. And so when we disattenuate, this coefficient, we get something that's almost twice as big, 60% bigger maybe, right? But when we correct here, remember what I told you intuitively, what happens when you have correlated covariates. That's going to further attenuate the results, but also inflate the effect of the covariates that you've included. And that's kind of what we see here. So when we correct the estimates in this model that included covariates, actually the relative importance of the parental education goes down a little bit. So it goes down from 0.15 to 0.11, and from 1.7 to 1.4. Not only that, but if you compare the coefficient when there are no controls to the coefficient once we controlled for parents, it still goes down. Parental EA does seem to be part of the pathway, but this is going down by a little bit less. And so the interpretation here is maybe different. We would, once we correct it, we would say, oh, maybe parental EA is less of an important pathway that describes why the EA PGI is explaining the, is predicting educational attainment. All right. Yeah.
Sorry, so I guess I'm probably missing something pretty important, but when I look at the original results, I can't shake the feeling that maybe there's some unobservable thing, like some omitted variable that's actually driving all this.
Driving everything.
Everything.
I mean, there might be. I mean, none of these things are causal, right? Like we've not controlled for parental PGI, for example, and so this coefficient here is going to maybe capture population stratification and indirect effects from parents and assortative mating, right? So I'm not going to try to describe how to interpret these results generally, because because maybe it's a bit tricky to interpret for all these reasons that you're thinking about. But to the degree that this is interpretable, I think there's a different interpretation once you do the correction. Right? And the results here are the same. What essentially happens here when you do the correction, because I'm just going to say what you see is the coefficients that are associated with either the PGI or their interaction both also increase again by about 40% or something like that, 60%. But you have slightly different but stronger results once you correct. So these corrections sometimes just will change the magnitude, but sometimes it really does change the interpretation of what's going on. Great. How long do I have today? I just want to make sure if I'm getting way behind. 3:10. Oh, we're great.
So this is based on the Becker's collection, not their papers collection.
So we did our very best to replicate exactly what they did. So these coefficients very closely resemble what they report in their paper. So these results, again, we couldn't exactly match everything they did. We did the best we could, and we were pretty close. So these are you could think of these as from the Papa, George, and Tom paper, and then this is our correction of the Papa, George, and Tom paper.
I only saw the left-hand side.
Yeah. So, yeah, right. This is the one that was in Papa, George, and Tom, and they didn't report this. We reported this in Becker et al.
So this is the PGI paper?
This is so this whole table is from the PGI paper.
I guess I have to read it, but this is very interesting. I was just wondering, what is this correction? How did you correct it?
It's a matter of, let's look at, it's the same principle as here, right? So the thing that causes the problem is that there's a bunch of variance terms that get carried around in, if you write out like the x prime x, inverse x prime y, like in those matrices, there's a bunch of these error terms that are hanging around that are just causing everything to be biased. And so for the correction, what we essentially did is we said, okay, let's just go into these matrices and just subtract out everything that looks like this. It's a lot of math. it's in the paper, but the basic principle is just identifying all the terms.
Are these observable?
So we do. Wait, is this observable?
Yeah.
Yeah. So the question is do we observe this? so we know where they are, right? Because we know that they just show up in terms where the PGI, that are associated with the PGI. It's like, imagine this. Oh, I don't want to erase this, but I'm going to do it anyway. So I'll just write it in the corner, right? So, we have our x prime x matrix, right, here, right? And, and then x prime y, right? So this is OLS. And so some of these x's, if you're doing a PGI study, are polygenic indexes, right? And so, like, let's say that this term here is the diagonal element associated with the PGI. So the interpretation of this thing here is the variance of the PGI. And the variance of the PGI is equal to the variance of the true PGI plus the error. And so what we do is we just kind of dive straight into this matrix and we subtract out the error from that term. And then, and then there's other things that happen when stuff is correlated. Dan?
It might help to point out that, the thing that we do is basically a well-known idea for correcting for measurement error. But you usually can't do it because you usually don't know how much measurement error there is. And what's special in the PGI context is that we have estimates of snip heritability, and we know how much of the variance is explained by the PGI. So from that, you can figure out how much measurement error there is, and then correct for it.
Yeah. I don't know if the people on Zoom could hear that, but the point is that these correction, the theory behind these corrections is well known. People have talked about it all the time, but it's a function. You need to know how much error there is, and sometimes we don't know how much error there is. But in our case here, because we know what the SNP heritability is and things like that, then we can use that information then to infer how much error there is and then remove it. Yep?
From Zoom, Emil left a comment. There's also a recent paper using sample splitting and IV to correct measurement.
Oh yeah, I was going to put a note in there about that, and I did not. Apologies to Phil. So alternatively, you could imagine sort of an IV strategy where the error in the PGI is a function of the sample that was used. So imagine making a PGI based on two different PGIs based on non-overlapping samples. Well, then the error in the PGIs for these two samples are going to be uncorrelated. And so you could use an instrumental variables approach and instrument for one PGI using the other PGI. And doing something like that will also correct your estimates. This is Phil's GIV paper. Dupree, Collinger, Burek. I think those are the three authors. Casper. The problem with something like that, though, there's kind of two problems. The big problem, though, is that it requires splitting your GWAS sample in half. Because you need to have non-overlapping GWAS samples to make PGIs that have uncorrelated error. And so, by splitting your sample in half, you worry that you're losing a lot of power. And so, I think that something like this that I described here, is a bit more powerful because we're bringing in additional information to correct for the error directly, rather than using, rather than kind of losing data by cutting it in half and using one as an instrument. Dan.
I think the advantage of that other approach is that you don't have to make an assumption about the SNP heritability. So basically, if you're confident, if you're willing to make an assumption about SNP heritability, then using that external information, as Patrick says, gives you more power, and you can use this method.
Yep. So it just depends on what assumptions you're willing to make.
How do we get the data on the GWAS for this correction?
So it turns out that this, the way that the method's able to infer how much error there is just a function of the SNP heritability. It's a function of the SNP heritability relative to the R squared of the PGI. And so what you technically do in the software is you tell it, here's my left-hand side variable, here are my covariates. And then you can either ask it to estimate the SNP heritability for you if you have individual data to be able to do that, or you can just say, this is what the SNP heritability is, and it just does everything for you.
From the paper?
Yes.
You can also set the R squared too if you have some reason to think that there's like I don't know, some better or more correct parameter for that.
So is that a problem that, like, if the underlying study use, say, the HRS sample, and I'm working with the HRS sample, like, is that a problem that the samples overlap or not?
Which sample overlaps with what?
So is there a problem that the sample that I'm analyzing is the HRS sample and it was used in the GWAS study where the heritability?
Yeah, so that would be a problem, right? So if your GWAS includes the health and retirement study, and you make a PGI for the retirement study, we're going back to the same issue of overfitting that we had before. Your coefficients will be biased upwards due to overfitting, and so ideally you would use a PGI that omits the particular sample you're testing in. I mean, if you use the PGIs from the PGI repository or the ones that are provided by the data sets, in principle, they've done the work of removing those individuals. And so, you shouldn't have that problem with the PGIs that these studies have made for you. But if you're making your own PGIs, then you should be careful. You should, double check your, look at the GWAS, check which samples are in it, and make sure that the sample that you want to study is not included in the GWAS that you're using to make the PGI.
Yeah, I think I understood that part, that the HRS, like, PGIs excluded the original sample, like they re-estimated the GWASs. But the heritability estimate, the reference heritability estimates that we can obtain as researchers will probably be based on the bias study that includes HRS, right?
Yes, I understand. So will it be a problem if... So the question is if, the correction requires an assumption about what the SNP heritability is of the phenotype. If you estimate the SNP heritability in the sample that you're using, is that going to create problems? I think actually no. I mean, in fact, maybe it's probably recommended, to be honest, because SNP heritability is sample dependent. So, some phenotype might have a certain heritability in one sample and a different heritability in another. And so if you assume that the heritability was, you used the ad health heritability in the HRS sample, then that could cause problems because it means you're going to infer the wrong amount of error. And so the software itself, the way that we wrote is if you actually have the individual genotype level data from ad health, it uses the ad health data to estimate heritability, and then it uses that to do the correction. And so no, I don't think it's a problem to use the same. We did it. If it is a problem, then we should fix it. The really important thing, honestly, is not even just that the heritability is right, but what you want is the ratio of the heritability to the R squared. And that's going to be a bit more robust from sample to sample. So if, what you could potentially do is, go into a different study with maybe a very large sample and estimate the SNP heritability and the R squared in that sample, and then just use both of those values, bring both of those values into, maybe your smaller sample where you're not well powered to estimate those things, or something like that. And I think everything still works out in that case. Great. Keep going. So here's the example. OK, so now I'm going to go through, I guess that first thing maybe should have been limitation 1, but well, it's not a limitation. It's opportunity. OK, so here's limitation 1. So one of the, I was talking to Ramona about this, I think. So one of the tricky things about PGIs is that the mechanisms of the PGIs, we don't really understand it very well, right? These PGIs use every SNP in the genome. And so, if we find that a PGI is associated with some outcome, what does that mean? And so if you want to use a PGI as a structural parameter or as an IV, these kinds of methods generally require us to have a bit more of a handle on, how these variables are operating. And just the PGIs use SNPs from all over the genome. And so we just can't know how they're operating, because different parts of the genome may operate through different kinds of pathways. On the other hand, in a lot of our research, we don't understand the mechanisms. And so, it's not clear that, PGIs are like uniquely limited in this way. We often just kind of throw in variables about, like we know that SES is really important for, later life outcomes, but we don't necessarily know why SES is important in that way. And so, PGIs maybe share that in common with a lot of the variables that we already use. We face a trade-off, right? With PGIs, it's great. We use all these variants. It increases predictive power. We have super highly predictive PGIs. Makes us very happy. However, we don't know what these variants are doing. So, you're trading off power for a bit of uncertainty of mechanism. We're learning. So it may be that over time, as we study these PGIs, we'll understand the mechanisms a bit more. Related to the comment that Roble made, if we made a PGI just based on, regions of the genome that, where we understand the function a bit more, then perhaps those PGIs are slightly easier to interpret. But this is just something to keep in mind. We don't really know what the PGIs are doing. Okay, the next is something we've also talked a little bit about. We're going to talk a lot about next week also with Elizabeth. But as a teaser, polygenic indexes are designed to be predictive in the samples where they were constructed, right? And we talked about how in order to reduce population stratification, we have to restrict to samples that are approximately homogeneous. And in practice, what that has meant up until now is that most of the research is done in individuals with European ancestries. And as a result, these PGIs that we're producing just don't do well at predicting phenotypes in samples with different ancestries than that. So in EA4, for example, in the AdHealth sample, or I guess 13% is HRS. In AdHealth, it's 16%, but only in individuals with European ancestries. If you look at the African ancestry individuals in those samples, it's we only get 1 to 2% R squared in those cases. It's much lower. So why is it lower? Well, there's a handful of reasons. So one might be people who have different ancestries likely are coming from different environments, and since they're from different environments, maybe the actual associations of these SNPs are different in those environments, and so we're using the wrong bees in that case. So that might be one reason. Another really big reason is that they also have differences in allele frequencies in LD. All right, so we talked about how when there are SNPs missing, it shares that information across to other SNPs in the genome. So we are capturing some of that, but how much sharing happens is a function of the LD between all of the SNPs in that region. And so if you then take a polygenic index which is optimized for certain for a certain amount of LD, a certain LD structure in European ancestry populations, and then you take it someplace else, it's not clear that it's pretty clear that it won't actually be optimal anymore. And so this seems this I think is also a really big factor in why they don't transfer as well. Yep.
I'm wondering if other things like height or weight, they also are poorly predicted in books? Oh.
Yeah, they are. So there's a paper by Alicia Martin, which I think might be on the reading list for the lecture that Elizabeth's giving next week, where she built a bunch of polygenic indexes for a bunch of different traits, and then used them to predict into groups with different ancestries. And so for example, anytime she used a polygenic index that was trained in European individuals and predict into African ancestry individuals, the predictive power was often 1/4 of what it was in Europeans, just for virtually all the phenotypes East Asians, I think the attenuation was a little less. Same with kind of admixed American samples. So that's a great paper. But yeah, just across the board, you see decreased predictive accuracy if you're moving from one ancestry to the next. Kind of 1.2 is one additional point, is that so this attenuation that we report here, you see this is like a 90% attenuation if you go from European to African ancestries for EA. Theoretically, you can go through and work out how much attenuation you would expect if it were just being driven by LD, and you only would expect like a 70% attenuation in that case. And so, which I think just highlights that both of these seem to be a problem for EA at least. It's going to be phenotype specific in terms of kind of the relative importance of these two things. But, so what do we do about that? Well, there are a lot of efforts to gather more data in more diverse samples. And so, if we get a large, 3 million person GWAS in Southeast Asian ancestry individuals, then maybe we'll start seeing really strong performance of those PGIs as well. So, there's some work to be done there. There's also methodological solutions that individuals are working on that allow you to more easily transfer information from summary statistics in one ancestry into another ancestry. And so there's work being done there as well. But this is super active. This is kind of cutting edge, just trying to figure out how to deal with this problem.
Yeah, I was wondering, like, in terms of like the distribution of like the outcome variables, for instance, EA, like in European ancestry versus like other ancestry. So variations in the distribution of like years of education, for instance, if there is substantial variation in that, wouldn't you say like the PGI would be more predictive for a certain part of a distribution versus the other, or maybe adjusting for a similar distribution would improve like how predictive a PGI would be, right?
So tell me if I'm. So it sounds like what your question is we do know that different populations also just have different phenotypic distributions. And so it may be that the PGI is very good at predicting differences maybe between like college, non-college, but really bad at between maybe lower levels. And so could that possibly be what's going on? And like, yeah, sure, it could be. How that would be reflected is, if there are SNPs that are more predictive of advancing in higher level education versus lower level education, then, and you have a population where most people have higher education, another population where they have kind of lower levels of education, that's going to be reflected in differences in the optimal betas that we're using. And so that's true, yes. So that's one way that there could be heterogeneity in the optimal effect sizes in the true additive SNP factor or the true polygenic index.
So when you're saying that reduction in accuracy is larger than can be expected by LD differences or allele frequency differences, so that basically leaves us only with environmental reasons for why for the discrepancy.
Yeah, I think that's the idea. Mm-hmm.
Isn't that counterintuitive given that they're in the same sample of out health, like they're all Americans, right?
Well, they are, but I think that the experience of an African American is very different than the experience of a European ancestry person, even if they're living in the same city. And so I think that's the idea. Is they face like in the case of African Americans, right? They face racism and discrimination and things like that in ways that someone with European ancestors probably doesn't. But also, it could be related to some of the things that Robo said too. Like if they also grow up tend to grow up in maybe poorer households or households with worse health, just there's lots of things that are different about. And this goes back again to this idea, when we say environment, we don't necessarily mean like a person's physical space. We mean everything about that person that isn't their genes.
I was wondering, could there be another biological explanation? I think in the previous lecture regarding, it was mentioned that we can look at how effects can differ between the sexes or between populations. Like with the waist to hip ratio, the effect is different in men and women, right?
Yep.
So would there be that the effect, the beta there is different across populations because of some sort of epigenetic mechanism?
Yeah,
I don't know if.
yeah, I mean, like, I guess, I mean, I would classify. I mean, the question is about, you know, whether other factors like epigenetics or things like that could also be driving some of these differences, similar to how maybe there's differences between sexes. But again, I would say that epigenetic type factors, they're not genetic, and so we'd classify them into this environmental umbrella. You know, I mean, there's also a question of like what causes those epigenetic differences to arise in the first place as well, right?
Well, in the case of the waist to hip ratio, it's probably other genes, right?
Okay, yeah, yeah. And so this is like epistasis, I guess, is what you're saying. So it may be it may be that there are interactions between SNPs, and so if there's a SNP that's more common in one population, and that SNP interacts with another SNP somewhere else in the genome, then the Bs would change in that case too, because this is just the average effect given sort of the expected you know, allele frequencies in the population. And so if there is epistasis, and then you go to a different population where allele frequencies are different, then kind of these average effects will change as well. So I mean, like, yeah, it's possible. I mean, you can't rule out explanations like that. I don't think that there's really any evidence one way or the other. I don't know of evidence. Yeah.
So in terms of like qualifying the R-square, like in European ancestry versus African ancestry, and seeing the differences, what are the covariates? Like, what other covariates we're controlled for before saying, okay, a PGI? For
these particular results?
Yeah.
So like, I think it's just the standard super simple, you know, age squared, sex, some PCs. I think that's it.
So wouldn't accounting for more covariates might tell us a different story?
So the question is, if we accounted for more other covariates, would that tell us a different story? Yeah, I mean, perhaps it would also just answer a different question, too, right? Because this is just about kind of the raw, you know, how much raw variation does the PGI explain? Whereas if all of a sudden you started including covariates for SES and things like that, then that's asking like how much variation does it explain net of these other covariates? You know, and maybe that's an interesting question that you might want to ask, but it's not the question that we were asking here.
In terms of so long as they're measured, the covariates, I mean, are measured in the same way for both ancestry, and we compute R-squares, net R-squares, after accounting for those very important covariates, wouldn't we see a huge difference? For instance, if we account for SES, like income or like family income, things like that, which we know predict like EA, if we account for those factors for both the European ancestry and for the African ancestry, and see the net change in our R-square.
I mean, like, I suspect that doing things like that, I mean, like, yeah, you'd have to be careful for all the reasons you're talking about. You'd want to make sure things are measured the same and stuff like that. But again, I think it's a different question. You know, I think you would still, I mean, the amount of attenuation would still be greater in the African ancestry individuals just because there's more noise as a result of just estimating in the wrong sample. But yeah, I think you're raising a different question, and part of the point here too is that answering that question is hard because of the differential attenuation between the two groups as a result of creating the PGIs in one sample and then predicting in another. Like these cross ancestry comparisons are really hard, like to the point that I don't. I'm not sure that it's possible to do comparisons like that, but we can at least say that, yeah, there is an attenuation. We know that at least part of that is just due to LD, and it's probably due to other things too, but it's tricky. This is all really hard stuff. How much time do we have left? I think I'm like 5 minutes. Okay, I'm going to move a little bit quickly through some of these. just so that we can get through everything. So first is, another limitation is that communicating these results is really difficult, right? And so we spend a whole lecture talking about how do you interpret heritability and what are the common fallacies that people use, and the Jenks critique and the Goldberger critique. All of those things also apply to PGIs. And so if you're trying to report research based on PGIs, you need to keep all of these common fallacies in mind. That's really tricky. One thing that is really common, well, not really common, but you often hear people refer to PGIs as like a measure of innate ability or a genetic endowment. But like, given these critiques, what does it even mean for a person to have a high polygenic index, given what we know about the interpretation of heritability? Like, what's so if I said, oh, I have or like we measure Grant's EAPGI, and it's like obviously like 4 sigma above the mean, right? What does that say about Grant? Well, I mean, I don't know. I mean, I like Grant, but it's I don't think because these genes may operate through the environment. It might be that he's getting a high draw because he's grew up in an environment that rewards kinds of things in the household that he grew up in. I don't know. It's all very tricky, and so you should be really cautious about interpretations of PGIs that are saying, oh, this is an innate thing. Because, like, what does it mean for something to be innate if it's interacting with the environment? And you change the environment, and all of a sudden it's different, right? Yeah.
John is asking, why hasn't Grant cured cancer yet?
I need like 3 more years.
He probably has, and he just hasn't told us. He doesn't want to make us feel bad. OK, one other point. So I told you that I was going to talk about why we've been using polygenic index instead of polygenic score. So a handful of us at the SSGAC, under the recommendation, actually, of a researcher, Martha Minow, she's a legal scholar at Harvard, they pointed out that scoring has maybe some value judgment, right? And so what would you think? What would someone think who's maybe think about my cousin who's a part-time real estate agent, and if she heard that all of these economists at these highfalutin universities are assigning education scores to everyone in the population, right? I think that has maybe a bit of an ick factor. It doesn't communicate what we're trying to do. It implies that maybe some people have more value than others because people associate scores with the football game, right? And so it's like, why do I get a low score? And so I think that some people had concerns that score had a value judgment, and so we said, well, maybe something like a polygenic index would be better. And so, hat tip to Martha Minow, who recommended that language. On the other hand, I don't think I had a point about this. This isn't without controversy, because you can alternatively imagine the poor graduate student who's just getting into this research, and they're reading papers about polygenic scores and polygenic indexes and polygenic risk scores, and they're trying to figure out what the difference is, and they're all the same thing. And so, proposing changes like this, we acknowledge are costly, but within the SSGAC, we at least thought that the potential societal benefits are hopefully greater than any costs it imposes. But so that's the rationale for the language that we've been using through the camp. Population stratification. I'm gonna skip this, other than just say that population stratification is still a problem with PGIs, and you need to control for it. And you can have stratification both in your discovery sample, so in generating the weights, but there can still be stratification in your prediction sample, and so you need to think about the stratification in both phases. Great. Ooh, I'm getting worn out. Okay. Alex is going to talk about this, so I'll skip this. Great. This is just based on the issue of let's say that you generate your polygenic index in a population sample, and so there might be bias due to gene-environment correlation. But then in your prediction sample, you use you control for the parental PGI as well, and so you're like, oh, now my results are causal because I'm using a family design with my PGI. But because you didn't use a family design in the GWAS, it gets a bit weird. I think Alex is going to talk more about this in detail. There's a paper by Jason Fletcher and co-authors that talk about this in even more detail. It's quite recent. Okay, I'm just going to go through one point because when people ask, like, what do you do with PGIs? Like, what's the value of doing work with polygenic indexes? One of the first things we often turn to is saying, well, what if you use it as a control variable? Like, that's a case where it's research that we all do already. Well, not that we all do, but that people do. That doesn't have anything to do with genetics. That polygenic indexes could potentially improve that research just by throwing in polygenic indexes as control variables in randomized control trials. And so just to explain why. So imagine that we want to know the effect of some intervention, T, some treatment, on some outcome Y. And so here's the model that I have in mind. We have our outcome Y. The treatment has an effect alpha on the outcome. And then we generally have a bunch of covariates. If it's a randomized trial, then T is going to be independent of everything because we've just randomly assigned T to everyone. Which also means that when we throw in covariates, like, we're not doing that to eliminate bias. We're already unbiased because of the randomization. But what these covariates do is they absorb some of this residual variation. And the reason that is useful is because if you wanted to think about what's the standard error on this alpha estimate, or I guess the sampling variance is what I've written here, well, it's equal to the variance of the residual divided by the variance of T times the sample size, right? And so you can increase your power by increasing the sample size, but you could also potentially increase your power by decreasing the variance of the residual. And so by adding in control variables that sop up some of this noise, we can get more and more power, right? I think that so that's the point here. And kind of a nice relationship you can think about between the two. If we can reduce the variance of the residual by some factor phi, then that's equivalent to increasing the sample size by 1 over phi. And if it's not very expensive to reduce the sampling variance, then it could be that we save a lot of money, research money, increase our power by a lot, just by throwing in controls rather than having to go out and gather more data. Yeah?
Actually, I'll let you finish this slide. I have a question.
OK. Just this one last point I wanted to make is that the important thing here is that our covariates in this setting don't need to have a causal interpretation. So all of these considerations that we were worried about with indirect effects and stratification, like, if they're just controls, we actually don't care. And so that, in fact, we maybe want there to be lots of stratification and indirect effects because really the only thing we care about is absorbing as much of this residual as possible. So this is maybe a case where stratification is great. Okay, I'm done with the slide. Do you have your questions still?
Yeah. I remember we had, in our readings, we had an article that looked at how sometimes scholars don't control for the covariates the right way. Sometimes it entails creating interaction terms between the key independent variable and the covariate. And I just had a question about that article because of how, sometimes you have reviewers that just keep on telling you, oh, add in these 10 other covariates, and then you're like, does that mean I have to add in those 2 covariates plus those 10 interaction terms? And so I just wondered, when I was reading the article, to what degree just adding in all those covariates increases your chances of finding an effect when it's just due to chance because you're adding in so many variables,
Yeah. So so I think you're talking about the Keller paper about G by E? OK, yeah. So there's a couple ways in which this is different. So in this particular case, we assumed that the treatment is randomly assigned. And so in that, and so this goes back to, it doesn't matter what we include as covariates in that case in terms of the interpretation on this. We're gaining a lot by saying that T is randomized. So the reason you'd want to add as many covariates as possible is because, more covariates you add, in theory, that will sop up more and more of this variation. To an extent, though, right? Because every covariate that you add removes 1 degree of freedom as well. So it's not necessarily totally monotonic. Like if you just started adding noise infinite, like just noise variables infinitely, then this should say n minus k is the point. So as you add more covariates, k is going to increase, which means that the standard errors might go down. So you want to hope that at least they're predicting some positive amount of this and greater than how much you lose by reducing the number of degrees of freedom. We'll talk about the Keller paper when we talk about G by E next week. So I just want to give, so the point here is that the gains from adding a PGI as a control will depend on two things. First, you want to know, what is the variance of epsilon if you don't have the control versus if you do have the control. And so what that means is that what you want to know is what's the predictive power of the baseline controls, how much of the variation do your initial controls already explain, versus how much additional information the PGI adds. So let's talk about the additional information, because let's say that some of your controls are correlated with your PGI. And so this is from EA3. What we did up at the top is this is the R squared of a handful of like standard covariates that people, social science covariates that people use as controls already. And so this first bar is if you have both parents' education. And so both parents' education explains about 20% of the variance in educational attainment. Down to like, income looks like it's, I can't see very well, but like maybe 8 or something like that. Marital status is almost nothing. And this is the EA3 PGI, and so it's explaining, 10-ish% of the variation itself. The question then is, how much does the PGI explain if you already control for these things? And so this bar here is how much the PGI explains by itself. And then over here is how much does the PGI explain once you've controlled for everyone's education and income and marital status. And so you can see it's not explaining as much, because some of the information about the PGI is encoded in the parent's education. So in this case, we get about 20% with kind of the most important parental education covariates, and then maybe we get about 6% on top of it with the EA3 PGI. And so we can use that and calculate what that's going to buy us in terms of power. So if the variance of the controls without the PGI is 20%, and if it's 26% with the PGI, you do a little bit of math, and that's equivalent to increasing your sample size by about 8%. And you just get that for free, as long as you're genotyped, right? But let's think about another example. Sometimes people do studies where we have information about, we want to say what's the effect of this intervention on test scores, and we have kind of a pre-intervention test score, and we want to look at the post-intervention test score. I looked up kind of what the retest reliability is on like IQ tests. It looks like it's about 80% for at least one of the things that I found. And so if we assume that the previous test score is correlated with the after the reform test score of about 80%, that means that the variance explained by covariates without a PGI is 80%. And let's say that absorbs almost all of the explanatory power of the PGI already, and so that adding the PGI only raises this to 81%. So the incremental explanatory power of the PGI is 1 percentage point. Right? In that case, you do some math, and even then, this is equivalent to increasing your sample size by 5%. So it's not nothing, even though we assumed that the incremental predictive power of the polygenic index is very, very small. I chose these numbers because I thought they were somewhat conservative. Like I suspect that this is, in fact, things are even better. I think that's all I want to go through. This is a nice paper by Dan Belsky where he tries to explore how the PGI is associated with a bunch of things like life course and mate choice and things like that. But I don't really have time to go through it now. But I encourage you to do it. Do people have questions? Yeah.
So I'm just talking to Raymond about this after this presentation. So suppose I'm interested in looking at ADHD polygenic index with some phenotype. And since we know that condition like ADHD, like it suffers from biotonic, so
that's a great question. So the question was about, there's a lot of phenotypes that are, genetically correlated, like genetic regions that are pleiotropic, meaning that there are genes that affect both ADHD and maybe other psychiatric conditions. And so, what that might mean is that if we wanted to do a study where we include an ADHD PGI, maybe we should also have PGIs for other psychiatric conditions as well to account for the pleiotropy. And if we do that, does that mean that we should also do this measurement error correction? And the answer is yes, right? Because to the degree that there's differential noise between these two PGSs, it's going to pass information back and forth in ways that are difficult to interpret. The tricky thing, however, is that the software that we wrote can't handle more than one PGI. And so the current version of what we have can't handle what it is that you're describing, even though what you're describing is something that probably we should do. Another thing that it can't handle that we really would like to extend it to do is, we've told you all that when you do these studies, it's really important to control for parental PGI as well. And it also can't account for errors. Like anything where there's two separate PGIs, it can't do that. But in theory, it wouldn't be that hard to extend it so that it could. Sorry.
We look forward to your pull request.
I know, that's right. Yeah.